Hello, Algebra 1 students, and welcome to your Lesson 8-5 video on linear, exponential, and quadratic models. So again, in this section, we're going to kind of talk about all the different functions we've talked about this entire year. So we did linear functions, we did exponential functions, and now we're towards the end of our quadratic functions. Let's remind you of some things, right? So when you talk about a linear function, right, that is your mx plus b, x is to the first power. And again, I should say y equals, but I'm ignoring that for right now. When you do your exponential function, you're doing a times b to the x. So now your x is in the exponent, right? And when we do our quadratic function, we're doing, I'll put ax squared plus bx plus c, but really you're focused on that x squared, right? So these are the three standard forms that you should have memorized going into your OST in April. Y equals mx plus b, y equals ab to the x, and y equals ax squared plus bx plus c. These are the three standard form for our functions we've talked about this year. So we're going to do a lot of table of values today and trying to determine whether this is a linear, exponential, or quadratic function. All right, so let's take a look at the next slide here. Okay, so this one says, how can you determine whether the data in the table can be modeled by a linear function? Okay, so in this table, we're going to focus on showing that this is a linear function. When you are doing the problems for Savvis, they will not tell you what type of function to show. They'll just ask you, is this a linear, exponential, or quadratic? So when you look for a linear function, what we are looking for is constant first differences in the y's. So I'm going to write down first difference. Right? So we are looking for the y's to change consistently. When the y's can change consistently, that is going to be a linear function. Now the first thing you should do is you should check the x's. So we check the x's first. And you look from -2 to -1, we are growing by 1. From -1 to 0, we are growing by 1. From 0 to 1, we are growing by 1. From 1 to 2, we are growing by 1. That is a constant change in the x. That must be the first thing you check. Once that condition is met, now we look at the differences in your y's. So from -1 to +1, we're going up by 2. If you can't do that in your head, you're just going to take 1 and subtract -1. You're going to take the second y value and subtract the first. That, of course, becomes 1 plus 1, which is 2. All right, but hopefully they're simple enough that you can kind of just count. So from 1 to 3, again, you're adding 2. From 3 to 5, you're adding 2. From 5 to 7, you're adding 2. What this shows is that you have a consistent first difference. So this is our first differences, and they are constant. So because we have a constant first difference of 2, this shows that these ordered pairs will represent a linear model. And this is the idea. Now I'm going to quickly put this in Desmos just to show you that it's going to be linear as well. Okay, so that's going to go away. Let's open up Desmos OST. I have the numbers in front of me, so I'm going to add a table. And we're going to add, so -2, -1, -1, 1, 0, 0, 3, 0, 3. 1, 5, and 2, 7. And again, you cannot judge just based off this, but you can see that they're kind of in a straight line. So this is a linear model. Perfect. Okay. All right, we'll come back to this with the next two. All right, so let's go to example 1b. So now it wants us to show why this is a quadratic model. Okay. So now we're looking at how can we show if something is a quadratic model. Well, when we're doing quadratics, because it is x squared, right? Quadratic is x squared. We're looking for constant second differences. So keep that in mind, right? X squared, quadratic, second difference. And again, it's the second difference in the y's. First thing you should do is you should check your x's, right? So if we go from 0 to 1, we're adding 1, 1 to 2, adding 1, 2 to 3, adding 1, 3 to 4, we're adding 1. So that is a constant change in x. That is good. Okay, so now we're going to look at the first differences. And again, hopefully the numbers are close enough that you can just use your brain. So from 3 to 9, we are going up by 6. And again, if you can't do that in your brain, come over here and do 9 minus 3, which is 6, or use decimals, right? From 9 to 19, we're going up by 10. From 19 to 33, and again, that might be tough for you, so just do 33 minus 19. Well, that's 14. You're going up by 14. And 51 minus 33, again, just a little scratch work, or you do it in Desmos, that's a positive 18. So you can see these are not constant, right? They're not the same number, okay? But now, I'll change my color. Now we're going to look at the second differences. So now we're going to look at the differences between these differences. So from 6 to 10, that's going up by 4. From 10 to 14, going up by 4. From 14 to 18, going up by 4. And there you go. We have a constant second difference of 4 because we have a constant second difference of 4. Constant second difference of 4. That means that this is going to be a quadratic model. Okay, let's show you what it looks like in Desmos, right? So we come back to here. Let's type in our table. So we're going to add a table here. All right, so it looks like I have 0, 3, 1, 9, 2, 19, 3, 33, and 4, 51. I have to zoom out a little bit just so I can show you, right? Now this is a little bit more tricky, right? Because you can't really tell that it's quadratic from here. Hopefully you can see that it's not linear, because if it was linear, let me see if I can use my pen. Right, if it was linear, it goes a little off like this, right? So hopefully you can see it's not linear, right? But again, if you connect them, that could be quadratic or exponential, right? If it's quadratic, it's going to do something like this, and if it was exponential, it'd do something like this, right? So we don't know, right? So again, that's why using the second differences or first differences is important. Okay. Well, let me erase that. Okay, last example here. So example 1C. So now, how do we show that something is exponential? Okay. So if we remember exponential, exponential doesn't have to do with addition or subtraction. Exponential had to do with ratios, multiplication and division. So what we're looking for is we're looking for a constant ratio between our y values. Notice here how the y values grow. Now again, you might have to go through all the differences stuff to figure this out. And I will do it the long way, okay? But when you're looking at ratios, so if you see fractions as your y values, or if you see decimals as your y values, that's a good sign that you're exponential. Okay, but these are whole numbers. This could possibly be quadratic, so let's go ahead and go through the whole process, and then we'll do the ratios in the end. Okay, so first thing you do is you have to check for the x's are changing. So 0 to 1 is plus 1, 1 to 2 is plus 1, 2 to 3 is plus 1, 3 to 4 is plus 1. So again, I'm thinking this might be quadratic. I know it's not going to be linear because they're not growing. Like from 1 to 2, it's a difference of 1, right? So I know it's not growing by 1, but it could be quadratic. So let's go with the first differences. So from 1 to 2, it's a difference of 1. From 2 to 4, it's a difference of 2. 4 to 8, difference of 4. 8 to 16, a difference of 8. Right? So the first differences are not constant. So now we look at the second differences. From 1 to 2, it's a growth of 1. From 2 to 4, it's a growth of 2. From 4 to 8, it's a growth of 4. So the second differences are not constant either. So now, this is when you go to the ratios. When you do the ratios, it's always the second y divided by the first y. So second divided by first. So we're going to do 2 divided by 1, which is 2. Then we'll do 4 divided by 2, which is 2. Then we'll do 8 divided by 4, which is 2. Then we'll do 16 divided by 8, which is 2. And there you go. These y values, second divided by first. So second divided by first, second divided by first, second divided by first, second divided by first. When you divide them like that, you get a constant ratio. And since this constant ratio of 2 appears, that means that this is going to be an exponential model. Now let's go ahead and graph this table real fast on Desmos. So again, I'll add my table here. Again, when the OST comes around, doing things in Desmos is going to be really helpful. So you have a table of values, you can always plug it in, right? And what was it? 416. So let me go back to home. So again, if you look here, you really can't tell whether it's going to be quadratic or exponential. Again, it could. So this is if I connect it. Sorry. So it could come back down like this and be quadratic, or again, it could come like this and then go towards the asymptote. So it could be exponential. So again, you don't really know for sure without testing it using the differences or the ratios. But again, don't feel like you always have to start with the differences. If you think that this might be a exponential, go right to division, right? Okay, last problem here. So it says compare linear, exponential, and quadratic growth. The graph shows population models for 3 cities based on data over a 5-year period. If the population continues to increase, when will the population of city C exceed the populations of the other 2 cities? So when you look at this and you're comparing an exponential, a linear, and a quadratic, you need to understand that an exponential always ends up growing the fastest. The fastest. So keep that in mind. An exponential always ends up growing the fastest. Growing. So if you look right now, and what I mean by growing is I mean by the y's. So if you take like this right here, see this line right here? This line represents when x is 1.5. Sorry, I chose the half, but I did that. Notice here that the exponential is actually the lowest. It's below the quadratic, and it's below the linear. The linear is actually growing the fastest right now, or it is the highest value right now in terms of the y. Its y right here is about 4.75. This blue y is about 0.5, and this green y, I mean, it's barely above 0. It's like 0.1 or 0.2. Okay? But now we're going to graph it in Desmos, and you're going to see what happens as they extend. Okay? So I'm going to take these 3 functions and graph them in Desmos. Okay. So the first one, f of x equals 3.2 to the x. Okay, it's going to be my blue one. Actually, I'll try to keep it the same color as it, so it's red. So I'll keep it the same color as the video. Then I have the blue graph, which is g of x. This is the quadratic, equals 0.25x squared. Okay, and again, notice that we only have the, we have both sides of it, but we're focused on the right-hand side, where it's positive. And again, I'll call this blue, I think. Maybe I won't. Yes, there we go, blue. And then the green one, of course, is our exponential. H of x equals 2 raised to the, notice it's in parentheses, so I'll put the exponent in parentheses, x minus 5. And again, we'll make this green. There we go. Okay, so that should match our notes, yes. So again, as you can tell, right, if I zoom in like our notes are, you can see that right here, right, the green one is below the blue and the red. But now as I zoom out, and again, this is going to become, and I scroll up. Okay, so notice right here, right? So at this point, which is like, oh, there it is. At 9.4 or 9.5, 22 and a half, now the green one exceeds the blue one. So now the green one is growing faster, and it's never going to stop growing faster than the blue. It's always going to be above. And then if you scroll up here, at 1032, now the green was above the red. So at that point, 1032, that is when the exponential, the green, is going to now grow fastest than any of the other ones. And you can see that it's always inside, right? So that means for the x value here, the green one was higher than these blue and red ones, which are down here. So I know you're looking at here and you're saying, oh, the red and the blue are to the right of the green. That doesn't matter. It's the x value doesn't matter. It's how big the y value is at these points. And you can see that these y values for the green are higher at a smaller x value. They get there faster. They get there quicker. Okay. So what I want to do real fast is I want to draw a bigger graph. Right. So I want you to try to draw that right-hand side on your paper, and I'll kind of model it right here. So let me get. So I'm going to use black as my axes, and again we can just go just like that. So I would like the red one to again go like this. I would like the blue one to go like that, and I want the green one to go something like that if you could. Right, so do your best there. Okay. But again, to answer this question, when will the population exceed the other two cities? You're looking for the point where it goes above the very last function, right? And again, I'll use purple. At this point, it exceeds the blue graph, but it is not until this point right here where it has exceeded both. And if I look back over here, that point where it exceeds the linear is going to be at 1032. So 1032. And that would be years. So the answer would be in 10 years. Okay. So again, no matter what you take away from this example here, always remember that an exponential graph is going to grow the fastest when compared to a linear or a quadratic. Great. Only one video for this lesson, so congratulations, you're done. We'll see you in class.